Yeah, thanks everyone for being here. So I thought last year's conference badge was really neat. And I've been studying computer architecture for a couple years now, and I thought, hey, why don't I dive into this with folks from the Supercon and get to show you once again just how cool it is and what are the neat things we can do with it. Okay. All right, I'm missing my title, but here's the goal for today. I want to talk to you about kind of the design of the Voya4. So we're going to talk about the ISA, or the instruction set architecture, and some of the design trade-offs that Voya Antonich had to make in order to bring to us this computer that we could all program. And talking about the ISA is going to also involve describing what registers and are in the Voya4, what's the memory model or the memory map, what instructions are available to us. And then we'll start to weave in how we might program the computer in assembly. I'll share with you what I like to call kind of idioms, which are just some short snippets of assembly language instructions that can form how we are able to do 16-bit math, 16-bit addition, and how we can use the instructions to do simple things like loops and conditionals and subroutines. And then towards the end, hopefully I'll get to show you how some folks from last year used the Voya4 to build some really fascinating projects, and hopefully kind of tease you a little bit with some projects at the end to really get your mind going and seeing how the Voya4 is not just this little kind of blinky lights toy, but it's a full computer. Getting into the architecture, and any of you who were here last year that were playing around with the badge might ask, why? This is so low level. What the heck, man? And I'd say I think my theory is just that if you write software long enough, at some point in your career, you're going to write a piece of software that whose security, its correctness, its performance depends on how the processor is executing your code down to the instruction level. And it's just a matter of time. When you get to that point. And when you do, hopefully at that point, you're not learning a computer architecture for the first time. It won't be the first time you've seen assembly language. So starting with a simpler architecture like the Voya4 is exactly how it's done in many ABET accredited computer science degrees, because many people still believe even if you write server level code, it's important to know how that code is actually executed on an architecture. And also I think it's fun, man. I love programming microcontrollers because you try to do a whole lot with a very little. And to me, like programming and assembly, understanding how the processor executes instructions is kind of the epitome of doing a lot with a little. All right, so let's build a computer. On the left should have been a screenshot of one of the manuals that Voya wrote. So you get a link down here to his project page that's got a bunch of really great manuals to describe exactly how the computer works. You've also got kind of a washed out link to the Hackaday GitHub page with an assembler and on all the examples that folks uploaded last year. I'm gonna try not to necessarily repeat this stuff. Hopefully I'll give everyone enough of an introduction to the Voya4 that even if you haven't seen it before, you can kind of follow along. But I'm gonna try not to spend a ton of time repeating all the great material that's already out there. And I don't know if these slides are public, but I'm happy to share them and the links with anybody later on. Okay, so the Voya4 has what we would call a Harvard architecture. What that means is that the processor in the middle that executes all these instructions talks to two separate pieces of memory. One piece of memory that holds all of the actual instructions, and a separate piece of memory that holds all of our data. The processor itself is home to the ALU, or arithmetic logic unit, that does all the number crunching. And there's a piece of control in there that kind of orchestrates the whole process. And then to make this computer actually useful, it's going to talk to some input and output devices. Now on the Voya4, we have what's called memory mapped I/O. And so what that means is that the processor doesn't have separate data lines and address lines to talk to I/O. It doesn't have separate instructions. The Voya4 reads and writes from memory locations that have been set aside, which are connected electronically to input and output devices. So this allows us to, or allows the processor to talk to the outside world using the same instructions that it would read and write from memory. All right, so if I had to give you an overview of the Voya4 ISA, this would be it. The instruction memory in the Voya4 that is supported is 4,000 words long, and each instruction is 12 bits wide. The Voya4 supports a data memory, which has 256 data memory locations that are each 4 bits wide. The processor includes an ALU that can perform these 31 instructions, and it produces 3 flags as a result of some operations that we can use to sort of branch on. And those flags are overflow, 0, and carry. And then the control unit's got 2 special registers, program counter and stack pointer. Excuse me. All right. So then the loop that the Voya4 does over and over and over again until the power is pulled is called the fetch, decode, execute cycle. And so in an infinite loop, the Voya4 will send its program counter to the instruction memory, say, hey, give me the piece of data that's at this address. That value, which is the next instruction to execute, comes into the processor. There's typically a cycle there where the Voya4 will decode that. It'll say, okay, what bits are in this opcode? What am I doing? And then it'll execute that instruction, which invariably involves some sort of reading or writing to memory, and in many cases also a slight change to the internal state. The memory mapped I/O are called the special function registers. Those live in the very last page of data memory. So you can see the 16 values there that control the processor. You can kind of broadly group them into 3 categories. The green box here are instructions that control the actual processor, so what's its clock speed and that sorts of things. I've got some registers that I've tried to highlight in blue that control the actual LEDs on the badge. And then I've got a number of registers that form sort of some basic peripherals. So I have access to basic timers, a UART, GPIO, keypad, and even a pseudo-random number generator. Okay, I wanted to make a quick note about the difference between architecture and organization, or architecture and microarchitecture. So far, when we've been describing the Voya4, I've not discussed anything about signal paths and multiplexers or anything like that. So this description of the Voya4 on the left that we use and we're going to program to is completely separate from any actual electrical implementation. This little picture I've grabbed on the right from a totally different processor would be, you know, one level down on the hierarchy. That might be how we would actually implement the Voya4. And believe it or not, there's a number of different ways we could implement potentially the instruction set architecture of the Voya4. I'll give you a quick example. So far we've been assuming, I think, that the instruction memory takes in 8 bits of an address in parallel and spits out, or sorry, not 8 bits, 12 bits of an address in parallel and spits out a 12-bit instruction. But that's not necessarily the case. Maybe we've got a piece of memory that is not 12 bits wide, but only 4 bits wide. And so maybe there's a little sub-assembly in the processor or in the memory that will take the program counter and sequentially spit out 3 sets of 4 bits that the processor then operates on. And how that's actually implemented in the processor as part of the organization. And so we're not necessarily going to get into that today. An example maybe in software is if I talk about a circular buffer or a queue, most of us kind of conceptually know what that means. But that isn't to say that we all have the same implementation in our heads when we talk about that. So today we're going to stay at the architecture level. All right, so let's write some assembly. Okay. You can't see it, but what? So this is going to be this will be like a storytelling experience here. Assembly instructions can be implemented or grouped into roughly 3 categories: arithmetic and logical instructions, data movement instructions, and control and branching. So we'll look at those 3 in turn. All right. So here you can kind of see the 18 or so arithmetic and logic instructions that are in the Voya4. So we can do addition, we can do subtraction, we can do a couple of logical operations. I've got a couple of instructions that do some useful things like incrementing or decrementing a register. And the format for these is if it's one of these instructions kind of in the middle here that specifies 2 registers, I will add or do the subtraction or the ORing on both of the registers and then store the result in the register on the left there. So I get a little example. If I'm adding R3 and R7, then I'm going to add those 2 registers together and store the result in R3. I've got this instruction here, DSZ, marked with an asterisk because DSZ stands for decrement and skip if 0, which is kind of a mixture of an arithmetic instruction and a control instruction, but it does arithmetic stuff, so I listed it here. Now, even though we only have 18 instructions on the Voya4, we can start to put some of them together combinations of 1 or 2 instructions to do other useful things. So the Voya4 doesn't have an instruction to necessarily do the bitwise negation of a register. But I can very easily implement that by just XORing R0 with all ones. Bits 4 at a time. If I want to add 2 16-bit numbers together, all I need to worry about in between each addition is just what that carry bit is, which is exactly what the add with carry instruction allows me to do. So what I've done is create a very a little Fibonacci sequence program where I've got 2 16-bit numbers stored in R0 to R3 and R4 to R7, and I'm just adding one to the other, adding that one back to the first, and then looping over and over again. So R0 to R7 sort of show the last 2 numbers in this little Fibonacci sequence. And this is also a great demonstration of the terms big endian versus little endian memory. The Voya4 only operates on 4 bits at a time, so if I'm working on a larger number, I have to describe how that number is organized in memory. If in my brain, the lower memory address is on the left and goes up to the right, so the largest nibble in my 16-bit number is on the left. We call this big endian because the largest part of my number is sort of stored in the lower memory address. But I could just as easily have sort of wrote this program as if I were working with little endian memory, meaning maybe it makes more sense to me to think of the lower memory address being on the right, aligned with the least significant nibble in my 16-bit number. I can do the same thing. I just kind of reorder my instructions a little bit. And so on any processor, when you're dealing with numbers that are larger than the bit width of the processor, and anytime you have sort of serial communications between 2 devices that exceed the bandwidth or the how many bits you can send at a time, you have to specify which is coming first, right? Most significant bit versus least significant bit. And in memory, that's big endian versus little endian. The Voya4 has got a great function called direct mode that lets us interact with the ALU directly, and specifically a handful of the ALU instructions. So that's a great way to kind of get into the actual bit operations on the badge. And then that's also the mode where we can sort of save and load programs and adjust some other features on the badge. Okay, I want to talk a little bit about instruction formats, and this will help us understand, I think, some of the design trade-offs that Voya needed to make. So we've already seen that I've got one set of instructions that require me to specify 2 operands, 2 registers, and so I've got one format up here in the blue where I get to specify a 4-bit opcode, and I only have room for those 2 4-bit registers. But I've got a handful of instructions that only really require 1 operand because they're all kind of implicitly either operating on register 0 or I only need to specify 1 register to increment it. And so those instruction formats are down here. You can see kind of in the last 4 bits is where I specify that value that I care about, and the ones to the left specify my opcode. And this is a great example of what's called an expanding opcode. So if I told you that the Voya4 had 4 bits to specify which instruction it could do, you might think it was limited to 16 instructions. But as we've just seen, there are certain instructions where I don't need the rest of my 12 bits to specify the things that I want to specify. So what we can do is say, well, for the instructions where I need to specify 2 registers, or I need to specify an 8-bit literal, those get reserved one of the 15 opcodes in the first 4 bits. But I'm going to save opcode 0. Opcode 0 tells the Voya4 what comes next is an extended opcode. There's additional information that will tell you what this instruction is trying to do. And that's okay because we don't need those bits in the middle to specify other values. The value comes in the last 4 bits. And this is what allows the Voya4 to have a total of 31 instructions available to it. Okay. So I want to talk a little bit about design trade-offs now. And just like the builder's triangle, where if you're building a house, you get money and time and quality and you get to pick 2, but not all 3. When we're designing a processor, almost invariably, if we try to optimize something, it's going to hurt our performance in some other capacity. And typically what we care about when we're looking at building a processor is how fast will it run programs when it's finally built? How much power is it going to use? How much might it cost to actually build? How easy is it or difficult is it to design? And how easy or hard is it to actually program? So we can see that when Voya picked this instruction format, we've got our opcode, which even with the expansion only allows us 31 instructions. And gosh, man, it would have been nice to have had a multiply instruction in there, right? or I don't know, like maybe there would have been another, we have a rotate right through carry. Oh, I wish I would have had a logical left shift or something. But that was a design choice that Voya made. We've got space to specify operands with 4 bits, so I can specify one of those first 16 memory locations to operate on in terms of my registers. Man, wouldn't it have been cool if those were 8-bit operands, right? Then I could specify operations to be done on the whole memory space. I've got room for 2 registers. So it's implied that one of those registers is used in the operation. Man, wouldn't it have been cool if there were room to specify 3 registers, right? I could add R1 and R2 together and store the results somewhere totally different. All those would have been cool. And in some ways, they might have produced smaller programs or more performant software. But the downside would have been that in almost all those cases, or I think in all those cases, the instruction would have got much longer, right? If I got a longer instruction, then I either need a bigger instruction memory, which costs more, or I can just fit fewer instructions in my instruction memory. It might have made, in the case of trying to expand out the opcode, it would have made the logic in the processor to decode that instruction more complicated, which might have made for a slower processor, or at least a higher costing processor. And in the case of the badge, I think Voya's primary goal was, how can I make a full computer that's not difficult to understand? And adding more instructions definitely would have, inhibited that goal. Another decision that was made was to make the instructions fixed length. In some processors, the instructions are variable length. x86, the processor in most of the Windows laptops we all have, has instructions that vary from 1 to 15 bytes long. And the nice part about that is, if I've got a really long instruction, then there's part of the opcode that just tells the processor, hey, the next 4 bytes, keep reading those in, because that's part of what we're doing here. And if I've got something really short, it can just live in a single byte. But of course, the problem with that is the design of that processor gets a lot more complicated, right? As that instruction's coming in, when the first byte is read, the processor doesn't 100% know how much more it needs to read in order to process that instruction. So ARM processors employ this fixed length instruction. The RISC-V processors have fixed length because that regularity helps make the design of the processor a lot simpler. Additionally, right, there were some design trade-offs made in the layout of the processor. So just deciding that the processor was going to be 4 bits long, that we were only going to be able to directly access 16 registers, and how much memory we had, were all design choices that Voya made. We could have expanded any of these. We could have made the processor be an 8-bit processor or a 16-bit processor. In real life, right, the trouble with that is now I've got twice as many or 4 times as many wires I have to route through my processor. I have to make my ALU 2 or 4 times as large. That increases the cost, it increases the complexity. Hopefully it improves the performance, but we don't know for sure. And definitely in this case, it would have not been able to fit that ALU on the front of that panel if it were even 8 bits wide. And so Voya had to make a lot of really interesting design trade-offs in order to bring this to fruition. And I think in a lot of ways there were some great kind of choices made to be able to make this be a capable processor, but still a processor that was easy to understand. Okay. The Voya4 has like 9 or so data movement instructions. So these are instructions that just sort of push numbers back and forth. We've got 3 instructions that just move values between registers or push values into the registers that will get used by the program counter. I've got a couple of instructions here in the middle too that will push data from register 0 or to or from memory. And in effect, this is how I implement my pointers, my indirect memory accesses. There's no compiler for the Voya4, just an assembler. So we have to manage our own memory directly. If I have a variable that I want to store somewhere, I have to, in my head, give it a memory address. And I can refer to that address directly using, let's see, values like 3F here to specify moving that value from R0 into that memory location. Or I can store 3 and F into registers themselves and say, hey, whatever's in this register, that's the address where we're going to grab some data or not. EXR and return are kind of interesting data movement instructions. EXR is short for exchange register, and it lets us sort of swap some registers between page 0 and page E. And I want to say this is not for saving registers in a subroutine, because once you go past the first level subroutine, you're kind of stuck. It's for I think, trying to kind of expand the number of registers you've got. So I think like one use case might be you could stash some addresses here in the alternate register set, and you could do some operations, and then when you were ready to push those out to data memory, you could sort of swap in those addresses and push everything out. Return is very clearly a subroutine return. So it is a control instruction. That's why I've got an asterisk here. But it's also, one feature of it makes it very useful for creating constant tables. So the return instruction will push this literal value n into R0 when it executes. And so we can create a table of data out of a series of return instructions. And if I sort of jump to one of these return instructions, the program will execute that return, come back immediately to where the call was made with some constant value in R0. And especially because the data memory is so limited, if there's like a bitmap that I'm trying to like push to the LEDs to kind of show a cool picture, or I've got a big long string of text, then I want to make that some type of constant data. Okay, the term addressing modes refers to how the processor is going to find what it needs in the instruction. And the Voya4 does this in a couple of different ways. So you can kind of barely see it on the left here. I've got the instruction move the literal value 4 into R0. The 4 in this case, in this upper box that's kind of washed out, the 4 is what we call a literal or immediate value because it's baked into the instruction, right? That instruction, when it comes out of memory, the last 4 bits are going to be 00, 0100, literal value 4. But there's also an operand that's kind of implicit. When the processor reads this opcode for move some literal number into R0, there's no R0 in that instruction anywhere. The processor just knows that when this instruction has that opcode, whatever value comes next is going into R0. Let's see, washed out at the top is what's called a PC relative. So we can potentially tell the processor to do is take a value and add it to the program counter, and maybe that's the value we care about. So when we execute a jump relative instruction, we're telling the processor to take whatever value comes after the opcode, add that to the program counter, and then go to that location. I can also refer to memory in an absolute fashion. So if I'm trying to move a value from memory into R0, well, I specify where in memory I'm going to get the value I need in the instruction. So that value in the instruction forms an address that I get where I get my data out of memory. And I would argue, in fact, that all the references to registers are also memory absolute instructions because they're all literally memory locations 0 to 15. The last one I think that the Voya4 uses is also called memory indirect. So in this case, if I'm grabbing a value out of memory whose address is specified at another location in memory, right? Then I'm sort of using a layer indirection to get my operand. One weird thing about addressing modes is that they're not industry specific. Every manufacturer has different names for these things, and there's an almost limitless number of ways that you can think about combining numbers in an operand or numbers with registers to get at data. We could have come up with another layer of indirection, a memory indirect instruction. We could have had a memory offset instruction where I specify where in memory I'm going to get my value, and then there's something in my instruction that adds a value to that, and that's the address where I get my memory. One differentiation that you get between processors, and one design choice that those designers have to make is what types of addressing modes do I think are going to be most useful to the people who are writing programs for my processor. And the x86 processor is notorious for having a move instruction, which is mega complex because it's got offsets and bit fields and shift amounts. And in fact, that instruction alone you can build a whole computer out of. But there's lots of different ways that you can address memory. Here's a cool example from a program called Tertis that Copagna wrote last year, which was a small version of Tetris. You can see that in this example, he's translating whatever is the current sort of Tetris piece that's falling down. And the Tetris piece is stored as a series of 4 x and y coordinates in memory that start at address B0. And so in this program, we start by loading B and 0 into registers 3 and 4, and that becomes a pointer to our coordinates. So we use this little move indirect function to pull in the first x value. We add whatever our offset is, and then we store that back to memory. Then we increment the lower address to go to B1. We pull in our y value, add the offset, and store that back to memory. And then we do that 4 more times for each of the four bits that are there. All right. We're going to look at control instructions now. So I would say that there are kind of 3 groups of control instructions. You've got instructions that change just the program counter, instructions that change the program counter and the stack pointer, effectively how we might call subroutines and stuff. And you have instructions that change the ALU flags. Golly. So you've got a couple instructions that will change the program counter, jump relative, skip, and decrement and skip if 0. So all these are going to be used to form more or less like your loops or your short conditionals. By combining, there's not like an actual like branch to some other address if some condition is met. So the way you typically form these is by using skip or decrement of 0 to jump over a jump relative call. So if we're not 0, we fall into a jump relative where we go where we need to, and otherwise we fall into our code block. We can also do what's called a long jump by writing to PCL. So if we target this memory location with a write, and that could be moving a value into it or incrementing that register, then that tells the processor, hey, we're trying to execute a jump somewhere really far in program memory. And so the processor will then grab these 3 nibbles, PCH, PC high, PCM, and PCL, and then just sort of push those into the program counter, and execution will start at whatever that address is. You've got a number of instructions that change the ALU flags. Just about any of the instructions that were on one of that earlier slide with all of my ALU instructions will update those flags. But I also have 2 more instructions that don't really have an effect on the processor other than to set those flags. So I've got a compare instruction, which will effectively subtract the literal value n from register 0. It won't change the contents of register 0, but whatever the result of that subtraction is, the flags will update to show that, so we can compare our 0 to a number and branch based on whether it's equal, which would mean that the 0 flag was set, or something else. I've also have an instruction that lets me test a specific bit in a couple of different registers to see if that bit's been set or not. Okay. This is not going to be good to see, but it's okay because I was not going to go over it anyways. So you can see this later if you want. This is how I might combine some of those jump instructions to do things like form a loop. In this case, it doesn't matter if this is a for loop or a while loop. The structure is the same. I'm testing whether a condition is true. If it is, I'm falling into my loop and then returning back to the top to test if that condition is true again. And writing flowcharts, I think, especially when we are writing assembly code, is just a great way to kind of think of this stuff. And so I've got a couple of slides here that show you how you might do that. you build that out of assembly. We can do the same thing with a conditional. The one weird part of a conditional is that I've got two separate code paths I want to execute potentially, but I can't list code side by side in my memory. It's got to be sequential. So I've got to get a little weird with how I jump around code blocks in order for this thing to execute. So in essence, I'm going to pick one of these two subtasks to come first. And then after I test my condition, if I execute subtask 1, I'll just sort of fall through. And if I don't, I have to jump around that first subtask to subtask 2 and then keep going. And once if I do fall into my first little branch, then I have to jump around the second one before I keep going with my code. And there's an example here of doing that for a very simple if-else statement. Okay, let's talk about calling a subroutine. So I want to talk about the mechanics first, which is I execute a subroutine by writing to the JSR register, and sort of like that long jump, if I target that with a move instruction or an increment instruction, that tells the processor, hey, grab those values in PCH, PCM, and now JSR, stuff those into the program counter because we're about to go into a subroutine. And as part of that process, the Voya4 will take the old program counter and save it in the memory page 1, this region allocated for my sort of program stack, and it'll increment the stack pointer to point it to the next free location. And so by doing that in my code, I can kind of jump to this subroutine. And then on my way back, I'm going to issue the return instruction. If I'm not using this for a table, then the value I stuff into R0 can be kind of whatever I want. But that return instruction will take the last value of the program counter that's in this program stack and then push it back into the actual program counter and decrement the stack pointer. So this allows me to return to the exact location in my code where I made that function call. Now, in order to do this properly, right, I have to set up kind of an interface, or you might imagine a very basic application binary interface, or ABI, which is how I set up my processor before I call this function in order for it to run correctly. And so at the kind of basic level, that means identifying a register where my input arguments go and where my return values are going to come back from. For more complicated functions, right, this would specify where multiple values may go, and if they can't all fit in the registers, where in memory all of my input arguments are coming from. And so in application binary interfaces that are defined for other processors, that's part of it, right? You have to specify, okay, if I've got values that either are coming into the function in these registers or they're on the stack somewhere. But just like before, I don't have a compiler, I don't have a data stack, so I can't just sort of push values onto or off of a stack that doesn't exist right now. So that means if my function here uses temporary registers or maybe calls another subroutine and needs register 1, then my function here has to save those values. There's an unwritten rule that my function, when it returns, it has to leave the processor in the exact same state that it was when the function first started. So the way to do this without a data stack is to just set aside some blocks in memory to say these belong to this, in this case, my square root function. It's going to save R2 and R3 into memory because we're going to use those when we're performing our calculation. And we're going to save R1 as well because maybe we need that value before we finish computing. And so no other piece of memory can touch those because those are used by the square root function. And it also means that I can't have any recursion. I can't even have my subroutine here call another subroutine which eventually calls square root again because those values would get stomped on and then my program would go off the rails. Here's a cool example of calling subroutines in Daemon Attack that was written by Unwired Ben last year. So this is like a little like base defender game. Here he's calling a function to move the enemies to some amount to the X. And so what he's got to do is pull into the registers these values which are stored in memory. So these are forming our input arguments. And then we call this subroutine. And then once it finishes, it will have updated these two values. So then we're using more move instructions to push those values back into data memory. Okay, I got a couple minutes left. We're going to talk about pushing the limits on our Voya4. And the short answer is the limit does not exist. The basic idea of Turing completeness is that it doesn't matter how complex my thing at the top of this pyramid is. If I can break it down into however long it takes me, if I can break it down into things that my Voya4 can do, then my Voya4 can do that thing. And believe it or not, there isn't a program you can think of right now that the Voya4 can't do. That's what Turing completeness means, and it's crazy. The one caveat is that we have to give it enough time and enough memory, which admittedly are big caveats, but to a mathematician, they're minor details, right? At least in terms of what the Voya4 is truly capable of. It's truly capable of everything, and I'll give you a couple examples. Number one, 12 years ago, a fellow by the name of Dimitri ported Linux to the Arduino. The ATmega 328 ran Linux in 2012 because this person ported it to it. Now, admittedly, it took 2 hours to get to a bash prompt and another 4 to load up Ubuntu. But it works, right? Because he did it. I don't think anyone, I would not have thought that you could run Linux on an ATmega 328 before I saw this, right? But that's what being Turing complete means. Admittedly, he does say that after this it was a little snappier. I think he said it was a couple minutes between typing a shell command and getting a response. So it was long, but it's possible. I'll give you one more example. I think many of us would say that maybe one of the most restricting parts of the Voya4 was just how much memory space we had. What if I told you that it was entirely possible to expand our instruction memory to 64,000 words and expand our data memory to over 2,000 memory locations? I'll walk you through how we do this. So number one, we are going to write a program for the Voya4 that emulates the Voya4. So we're going to do a little inception piece, right? Yeah. I've got a Voya4 here, which itself is just a processor. It's going to talk over, we'll say UART, to a piece of memory that has my instructions and my data. And you can't quite see it here, but I've got like an assembly program that sends out a program counter over the UART peripheral to my memory system, receives an instruction back. It increments its little internal program counter, and then based on whatever the value in those first 4 bits are, it runs this piece of code. And so I've got my memory here that's storing my instructions and my data, and I need on the actual Voya4 over here, I've got some memory set aside to sort of emulate the registers and the program counter and the stack pointer that I'm sort of simulating on my Voya4. All right, step 2 is to make the program counter 16 bits long. So I'm just gonna, when I send out the program counter to get the next instruction, I'm not gonna send out 12 bits, I'm gonna send out 16. And that involves expanding out this little program counter in my memory to 16 bits. And I can do that. And what it would do is it would sort of give me 16 blocks each of 4,000 words. And when my Voya4 got to the last address here, 0FFF, instead of adding 1 and rolling over back to 0, sort of reaching the end of my memory system, it would add 1 and sort of move into this next block here. It would be 1FFF. That's not a huge gain. Those blocks are still kind of segmented. It's going to be difficult for me to kind of jump back and forth between them. So I'm going to make one more change to the Voya4 ISA. And what I'm going to do is take register 9 here, and I'm going to call that register PCT, or PC top. And so now my program counter is formed from these 4 nibbles, PCT, followed by PCH, PCM, and PCL. So the rest of the instruction set architecture is the same. It's just that when I make long jumps or subroutine calls by writing to the JSR or the PCL register, I just have to modify my program a little bit so that when it does that, it's now going to grab a 16-bit PC value and send that to my memory. And so now it might take a little bit of hand assembling because the assembler doesn't support this, but I can write long jumps and subroutine calls that expand out all the way across 64,000 memory spaces, 64,000 instructions. And with one little trick, I can kind of expand my data memory also. To do that, I'm going to use a technique called banked memory. And so I'm going to take this little register right here, or this little piece of memory, and I'm going to call that my bank number. So that value, that spot in memory can be anywhere from 0 to 15. And I'm going to say this rectangle up here is my sort of shared memory. The rectangle underneath it is what's called banked memory. And which of those banks is sort of in play at any point in time is dictated by the value in this little box right here. So I can reference 16 different banks of these these areas by just changing the number in this little box right here. And that gives me 4 plus 8 times 16 pages of memory that I can reference, which is what allows me to go up to 2,000 words. And I might have to do a little bit of data shuffling to go back and forth, but I can totally do that. All right. So hopefully, despite the slides, I've piqued y'all's interest a little bit and shared with you how cool this device is and what are all the things you can do with it. I'm going to share with you a few resources and get out of here. Number one, Voya was kind enough to share his design files with me and help make sure that I had the correct ones. So if you want to get one for yourself, you can do that. I've got about 125 on order that'll be coming in the next week or so. And so don't be dismayed if it says out of stock. I'm just waiting for those to come in and you can buy one. If you're interested in yeah, I'll share that with you later. I'll put that back up, don't worry. If you're interested in learning a little bit more about computer architecture, these 3 books I feel like have been super useful for me. They've been very approachable, very clear, and 2 of them, this one here comes with its own website and eCoursera course. This one here was the textbook that I used for my computer architecture course last year at West Point, and so there's a website down here. You can see the course website where I shared computer architecture stuff with my students. If you want to get your hands on actually building a processor out of chips, there are ways to do that. I thought these 2 were kind of the coolest. The 4-bit CPU by Big Mess of Wires here doesn't come with a kit actually, but it's fully described in the website. And Ben Eater is famous for having a whole series of kits about building an 8-bit computer on breadboards. And with that, I just want to say real quick thanks to Voya for all the great work he's done on this badge and many others. Thanks to Hackaday and Supply Frame for the Supercon, and thanks to you all for hearing me blather for 40 minutes. I hope you all enjoy the rest of the conference.